Well, good morning. So please keep answering if you haven't done it yet. Question number one, evidently many students got so confident after the exam they decided they don't need lectures anymore. Well, a couple of things I usually say after the first exam, because it's the first exam. First of all, I know with absolute certainty there are students who are satisfied with the grade. So if you are satisfied with your grade, that means do whatever you've been doing, it works for you. That's it. If you're not satisfied with your grade, that means you should reflect on last 2 weeks and try to figure out what could have been done differently. So this is the copy from the first lecture. This is how the total grade will be calculated. So right now, everyone can make a rough estimation, assuming that you don't lose any points for labs, homework, and attendance, and assuming that your exam 2 grade and exam 3 grade might be within the same range, you can make an estimation. If your estimation, again, satisfies you, just keep doing what you've been doing. Otherwise, you, have to make a choice. What to do? And I'm not going to tell you what to do. I don't know you. So this is on you. Now, the first exam always gives the most number of feedbacks. After the second exam, people just give up. I always read them. I like reading them. And basically, since I've been reading these feedbacks for years, I'm just trying to find something unusual and unexpected. So far, again, everything is very natural, very similar to what's been happening before, which is a good sign, of course. Anything unexpected would have been a bad sign. And I'm not going to address all of them. What I usually do, I read them, and if I don't see any personal information, sometimes people leave some personal information. I don't know why. It says anonymous. So, but if I don't see any personal information, I scan it and I put it on the blackboard so you can read what you or other students say. Of course, when you talk about lab TFs, some people love their lab TF, some don't. When having a lab TF, it's like buying a lottery ticket. That's it. They all come from different countries with different experience. I've met most of them just 2 weeks ago, a day before the course, and even I cannot teach them what they can't do or cannot do or can do or how to do in 2 weeks. It's impossible. So it means you should be as active as possible. Anything which you feel doesn't go the way you want to go, step up and tell them, because they have to help you to do what you want them to do. So if you want them something to do, but you don't say that, they don't do that. Some of you are even older than some of those guys, so you may have more experience in general with organizing things. So help them help you. Very standard note that for me, this all is happening too fast. Well, I agree. For some of you, it might be happening too fast, but seeing things like fast, slow, hard, easy, those are not objective things. Those are subjective things. It depends on feeling. And again, as I've mentioned before, the amount of time, the amount of effort required for this course is fixed by the syllabus, approved by officials, and there is not much wiggle room here. It's just the way it is. Someone asked me when I solve problems to show if that problem will be on the exam or not. I'm not going to do that. Now, so there is a sentiment that I might spending too much time on simple problems, and I would need to spend more time on complicated problems. Well, first of all, simple and complicated, again, is subjective, and I'm not solving a problem. I'm presenting a strategy. I saw that word again and again. So if you catch up with a strategy on a simple problem, you should be able to apply at home. That's where complicated problems should be done, using the strategy learned in the class. That's how it's supposed to work. If we had twice more time, first I could spend time on the simple problems, and then I could spend more time on more complicated problems. But it's a time-limited course. So, plus, it's important to make a kind of switch in your view on what's happening when we solve a problem. We don't solve a specific problem. Yeah? It's not like a following Google map, do this, do this, do this, you're going to be there. No. All the questions, all the steps we're covering, the same, which should be applied for any similar problem. The key word is similar. And this where homework gives you an opportunity to practice similar. So this is a homework, and you ask this problem, what is it similar to? And then you apply the strategy. Now, explain mathematics a little more. Well, that's what office hours for. This is not math class, I'm sorry. I can't spend too much time on mathematical details. Again, it's a time-limited issue. I feel like practice exams did not compare. Yes, it wasn't a goal to show you an exam which could have been the same as your actual exam. Those practice exams, like practice problems, just some additional practice tool, that's it. The fact that they've been called in exams in the past mean nothing. It's just another set of problems. And feeling is not for physics. The exam was too long. Well, Most of reviews said that exam was fairly fair, which agrees with what I feel. But again, too long, too short. First of all, it's subjective, but based on what I've seen, and I've seen that at the end of the exam, I would say 60 out of 80 people left already. I don't think it was too long, objectively. We need, first of all, again, it's always there. A note about handwriting. With my eyes and my fingers, that's the best I can do. But I also would ask you to do the same, because I just couldn't read, couldn't understand some of yours. But I understand this word, mkat. And if you read the syllabus, it says this is not a prep for MCAT. This is a prep for the prep course for the MCAT. See the difference? Now, TF should not abuse power by assigning more problems. I really don't understand what it means, because they shouldn't, and I don't think they do, but this is something I would really like to get into. If that is happening, just tell me more, because I don't understand how that might be happening. I would need a specific example. In that case, I would be happy to move. So, by some reason, someone left a picture of a free body diagram. I don't know. Maybe it's a good sign. So again, you can read it later on. And if you have any question, today, within a couple of hours maybe, I will post the solutions. So that's give you an option to check your work with the solution. After that, you can see me and you can ask me, this is the solution and this is my work and this is the same, but by some reason I've lost some points, and that's something I can do. But the only person who can do it, me. So don't even bother talk to TFs. And grading mistakes do happen. Grading is not a science. It's a combination of science and art, and requires practice. So, and I don't grade. I want to be impartial. So TFs grade, well, normally. Sometimes when TF is sick or something, I have to step up. But normally, I don't grade. So if anything is wrong with your grading, it's not my fault. Again, see? This is what we're going to start talking about. So don't read it. It's just an example of another amount of information we should finish by the end of the second week. And first we start talking about the homework. You should start doing it as fast as possible, as soon as possible. I mean, it means after this lecture, you already will be able to do something. And this slide tells you the best case scenario, yeah, recommended, and the actual deadline. And again, miracles do happen. Sometimes WebAssign changes deadline. I don't know why he does it. So, but this is what I would recommend to follow. Friction. What do we know about friction? A lot. First of all, it exists. But more importantly, we know that there are two types of friction. All right, first of all. If you are here, but you didn't take your exam, please raise your hand. Did you do this or this? Yes. Okay, so, all right. So these people are absent. And you can pick it up after the exam, after the lecture. Just come, yeah. Just after the lecture, just take them. I just want to clean up the bench. So friction. What do we use this for? This device is to measure force. So we can use this device to measure force I am applying right now to this rope string. And that string now is applying the same force to this box. So the force is not zero, yeah? But the box is not moving. Why? Friction. That's the only reason it remains at rest. So there is gravity, normal, tension, and friction. But if there is no motion, this force of friction, which prevents it from moving, has a name, force of static friction. And the word static means no motion. And if I start applying force which is stronger and stronger, at a certain point it starts moving. So there is a critical value for static friction. And if we go above that, that's it. We can, oops, yeah, more friction here. We can make it move. And of course, this force acting on a moving object has a name, kinetic. Kinetic in Greek, moving, so kinetic friction. That's what we're going to talk about mostly. The force of kinetic friction. How to measure, how to calculate. Well, how to measure. The easiest way is to move it with constant velocity. If velocity is constant, the acceleration is zero. You may thought, well, exam one is done. I can erase everything from my memory. Not yet. 4 more weeks. Actually, some of the stuff, if you stay here for 106, you're still going to use during like first 3 weeks. So don't erase yet. If acceleration is zero, that means net force is zero. That means gravity and normal cancel each out, but also friction and tension cancel each out. So if I move it with a constant velocity, this also is the magnitude of friction. And of course, if I move it with acceleration, we can apply Newton's second law. Well, we can study what it depends on. We can add some weight and see how it changes the applied force. Many examples show double the weight, double the force. Turns out it's not about weight. If we take this setup, walk to the elevator, and measure when it starts moving up, turns out the force of friction will be even larger than now. So it's not about weight, it's about normal force, the force of interaction between the surface and the object. Same on incline. Normal force is responsible for force of friction. And this fact tells us that we need a new physical quantity to relate those forces. That physical quantity has a name, coefficient of friction. Well, technically a coefficient of kinetic friction, but we usually just say coefficient of friction. We know what it means when object is moving, it's kinetic. And that's my question to you. What do you think about the unit of this variable? This is an official definition of this variable. This is a Greek letter. People call it mu or mu. Doesn't matter. But not mu. Different textbooks use different symbols. This usually means friction kinetic. This is just force of friction. Every time when you write a variable, you just need to know what it represents. So you need to be able to say out loud, this represents normal force, and that's what we call coefficient. This is a definition of this. If we want to use a definition, we just have to solve for this and see what's happening. And what is happening? I don't know. yet. So, and again, possible answers. It's booting up. You know, I don't know about you, I love being alive. And I know it's limited. So I cherish every second. And when things which supposed to work fast, supposed to work slow, that makes me angry. That's it. So it's not you. It's this thing. If you ever see me angry, it's not you. It's never you. For the record. That's a very good distribution. Two people still in the fog. I'm sorry. Get back as soon as possible. And the answer number 5, I think, is the absolutely correct one. It has no units because we have force on the right, force on the left, newtons, they get and cancel. This is a rare example when a physical quantity has no unit. So it is just a number. And, well, of course, we have situations when we know that number and have to use it, or we have to find it. This is a situation where we need to find it. And again, you see, you may have thought, well, I can forget everything I've learned before the exam. No. This is just a copy of the picture from one of the slides we used before. We just added friction to it. Well, so what do we do? What is the key word? One single word which trumps everything. No, that would be the second. So, any other suggestions, please? What do you think? Yeah. No. It's a tricky question. That word is written in invisible ink. You should read behind or between the lines what this problem is about. No? Yes? Mm-hmm. Not yet. Force. Do you see that huge green arrow? That is a force. That means, as long as we said that, we just have to apply all strategy related to forces. And only then we can start thinking, well, how can we add to the strategy one new equation? It's just one new equation about specific force, force of friction. So technically, it's nothing new. And when we solve a problem related to forces, what is the first thing to do? What do we do? Diagram, of course. So we just have to follow this strategy. First step, well, we read it. We start imagining it's already here, but it's not a diagram yet. We're missing other forces. So that's what you're supposed to be doing right now, and I don't see anybody drawing free body diagrams. What does drawing mean? What do you think? This word, to draw. Well, it's not like you want to shoot someone. All my joke is deadly, so. Drawing means what? Using a specific device which can leave lines visible to us. That's it, what it means. So, a pen or a pencil. How do we draw a frictional force. In which direction? How do we call that direction? I wouldn't call it X, no. There's a much simpler everyday word we usually use for that direction. Oh, that's geography. How do we call that direction? Left. This is how the brain should work. You need left? Well, nothing negative yet. I don't even have the axis. You need to search for easiest way to describe what's happening and then build on that. That's the force of friction. And we move it. The velocity is constant. We know that means acceleration is 0. So, see, some things here come from our experience and some from our knowledge. And experience and knowledge, slightly different things. This is the knowledge from the previous study. Experience is something from our everyday life. Now, we can say that, yes, it would help to add 2 directions which we use. Now, again, based on our previous experience, we can, it doesn't have to be that way. Some people don't do that, but I recommend to replace an actual force, to replace it with the 2 components of that force, which we usually call X and Y. Why? It's easier from my point of view because now we can see what's happening. There's normal force pointing up, and there is force of gravity, and that Y component pointing down, and they have to cancel each other out. But also, there is friction pointing left, an X component of the force pointing right, and they also have to cancel each other out. So we can write, and this is a straightforward application of the Newton's second law with the fact that net force has to be equal to 0. Relative to the x-axis, we can write magnitude of x minus magnitude of friction equals 0, or we can just write that this component should have the same magnitude of this. Relative to the y-axis, we can write that normal force should be cancelled out by 2 forces directed opposite to it. And that is physics is done. Basically, we just can copy and add to this set of equations 1 more equation. So now we have 3 equations. Oops. See? Why would it call it 3 if it's 2? I don't know. This is just a fact. But sometimes our brain plays tricks on us, so that we have to pay attention. This is what I wanted to write. After physics is done, we still can do some more, not related to physics, geometry, because we have a triangle. We have a triangle which relates all these components, and force F, Fx, Fy, those are magnitudes, 30 degrees. So Fx supposed to be equal to F times cosine. Fy supposed to be equal to F times sine. And now we are done completely. So we just need to figure out how to relate all these expressions together to solve it for this variable. Well, clearly this variable should be equal to this ratio, friction, over normal. friction, 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 friction. That comes from equation 3. From equation 1, friction is equal to x. From equation 2, normal equals Fy plus mg. And now from geometry equations, F times cosine 30, F times sine 30 plus mg. I'm not going to finish calculation. Now you just have to plug numbers and use a calculator. But I want to ask a question. Can you cancel these two variables, f in the numerator and f in the denominator? No, you can't. And I've seen that before. That would be a mathematical mistake. You cannot cancel because this term doesn't allow to do that. You pushed a box. So you see, it's a terminological difference. Pushing means a continuous action. Pushed, that means this. So after you supplied some velocity, it's been sliding, slowing down. Why? Because of friction, of course. So free body diagram, of course, now is easier, and you should draw it. And we have gravity, we have normal, we have friction. Do we have any other forces acting on it after it's been pushed? No. That's important to remember. All we have is just velocity because it slides to the right. But what is the direction of acceleration? Left. Because it slows down, acceleration is opposite. Eventually it stops. Let's say here. So the final velocity is 0. The initial velocity 5. What are we looking for? Distance traveled. Okay. Well, again, there is force. And that means we have to start from strategy applied to object under influence of forces. Free body diagram, Newton's law. Newton's law. Newton's law. Again, vertically, normal and gravity cancel each other. By now, we should technically see it clearly. It saves time. Normal is equal to mg. All important things are happening here relative to x-axis. So what is happening? Well, there's only one horizontal force, and it points to the left. And acceleration points to the left. That's our equation. Now, well, every time after we just wrote something, we ask to ourselves the same question again and again and again. What can I do now? So, what can we do now? Can. That's this means wherever we say is a hypothesis or a guess or a try. So we say that, we try that. It works. We ask a question, what can we do now? We say it, we try it. If it doesn't work, we ask a question, what can we do now? We try something new. If it works, we ask a question again and again until we finally have it solved. That's how it works. So Any suggestions? What can we do now? Yes. Perfect. It's a loop. What can we do now? You can't ask a question to a question. To a question, you have to make a statement. What can we do now? We can use that equation. Can we? We don't know, actually. It's a hypothesis. We have to try it and see. Friction should be equal to the coefficient times normal. So if we try to use this equation, the acceleration should be equal to the coefficient times normal over m. That's the magnitude of acceleration. Okay. I just finished writing an equation. See, my hands don't move anymore. What question should I ask? What question should I ask right now myself?
What are the values?
No. What can I do now? And now what is the answer to this question?
Plug in values.
Let's see what we can plug in. 0.4. Do you know a value for Fn? No, you don't. I don't see it on the screen. Where is Fn equals 5? Fn equals million? No, you don't. M. Do you know the value for M? M. 15. That's my mistake. Technically, we don't need it. I forgot to erase it. It makes your life easier, but it doesn't affect the solution, as we will see in a minute. Okay, 15. Fine. What can we do now? What can we do now? We still have one more. Yes? Exactly. And now, when we search for the answer to the question, what can we do now, we always use hints. Something which hasn't been used yet. So, mg, g, or 0.4 times 15 times 10 over 15. So this is what, actually, in a part of the reasoning, important fact. Turns out we don't really need the mass for this particular problem, and 0.4 times 10 is 4. That's the acceleration. But the question is about the distance, not the acceleration. So, what can we do now? Exactly. We know that on one hand, net force, mass, acceleration are related, and we just use that relationship. And net force is related to specific forces like normal force or force of gravity or force of friction, and force of friction is related to the coefficient of friction and normal force. But on the other hand, there's one variable which also related to another set of variables like initial velocity, final velocity, time, and also they might be related to displacement, directly or indirectly. So we've used one set of connections, but we still have another set of connections we can use. And that set of connections, again, comes from the equation sheet number 1. This is what we have. The initial speed is 5. The final speed is 0. The distance traveled is unknown. Acceleration points to the left. The magnitude equals 4. We can write the motion equation. We can write the velocity equation. And we also can write the third equation, which has no name. v squared equals v initial squared plus 2 times a plus delta x. And that's what I want to use because it gives me the answer immediately. This is 0. This is 5 squared plus 2 times L. And what number should I write here for the actual value of acceleration? Or we call it a component. What number? What? Negative 4. That's it. Nothing new. Just reusing what we've learned before. So the distance will be equal to 25 over 8. Please. Three-point? What's your number?
3.125.
Yeah. Because if we divide by 8, last digit's always. All right. Any questions? See, I promised you that time would come that we would use both sets of reasoning, both sets of variables, one set related to force and acceleration, second set related to acceleration and velocity or distance. And this is an example. If I promise something, I deliver my promise. Yes?
So does the v squared, like I think we use average velocity there, but you
No.
can stick in the final?
No.
Okay, so it's just v final.
This is final, initial. This equation has no averages. Everything instantaneous except this variable. This relates 2 points, initial and final. And acceleration, of course, assumed to be constant, and it is, because 4 is just a number. 4, 4, 4, 4, 4. Well, now we're going to talk about energy, work, momentum, and we're going to use sometimes what we've learned about friction. First, a quick general review. I'm throwing in some definitions. By the way, I forgot. Please, could you remind me, what is a definition?
Something agreed upon by a lot of different people.
Thank you. Now I know. So, all these equations, something which people have been agreed upon for hundreds of years. And at this point, all we have to do is just memorize them. And we need to know the exact meaning of exact variable. That's it. The only problem is that sometimes people use different symbols. For example, this symbol stays for kinetic energy. But also people write sometimes energy kinetic. M is not meters here, of course, mass. This V is velocity of an object squared over 2. And if we use International System of Units, the official unit of energy will be a joule. But in everyday life, we also have a different unit, calorie. If you buy food, you can read the amount of calories it supplies. That's standard conversion factor. 1 calorie is about 4 joules. This, gravitational potential energy. Also people use a symbol like energy potential, energy gravitational, or U. Doesn't matter. This is an official definition for gravitational potential energy for an object which is close to a surface. Mass, 10 or 9.8. Y. Y is the y coordinate of an object relative to the vertical axis directed up. That's important. Work. A work is not something we do and getting paid or not. In physics, a work is a number which is supposed to be calculated using this equation when the force acting on an object remains constant. So this is efficient definition of a work done by a specific constant force. What kind of a force? Doesn't matter as long as it is constant. Constant force. And this is the magnitude of that force acting on an object, displacement of an object, and this is an angle, well, cosine of an angle between force and displacement. For example, if I pull on a string, there's gravity, normal, friction, and strain. 4 forces. So each force does its own work. And for each force, because these forces are constant, we can apply this equation. We just have to, if it's a force of gravity, we have to use magnitude of gravity and an angle between gravity and displacement. If it's force of tension, we should use magnitude of tension and angle between displacement and force. And wherever it is. And last equation is a definition of what we call linear momentum. Now, please look at these pictures and tell me, one, the most important difference between this variable and all other variables. Yes?
Momentum's a vector.
Exactly. So when we talk about work, energy, those are numbers, positive, negative, whatever, 0. Momentum is a vector, it's an arrow. Now, when an object is, well, something is happening to it, moving or at rest, kinetic energy of this object might be 0 or not 0, might be changing or not changing. There is a law, that's a law. The law is a result of many, many experiments, that's it. So people have been measuring how kinetic energy changes, people have been measuring individual work done by each force. Turns out, no matter what's happening, this always true. What does it mean? Well, this means the change in the kinetic energy. And in physics, the word change always means difference, final minus initial value of something. This symbol represents the net work or total work done by all forces acting on this object. But we already know what this word net means, just the sum. If we have 4 forces acting, each force does some work, so we have to add the work done by first force plus work done by second, third, fourth. In the end, we get a number which we call net work or total work. And the change in the kinetic energy of an object always equals the total work done on that object. This is actually, we're going to talk about later, the law of conservation of mechanical energy, just written in a different form. And this law has a name, work kinetic energy theorem, or WKET. That's it. Again, just a definition of a shortcut for this. And of course, we know that every device we use has a special label which says power. Power is just average work done every second. That's it. That's an official definition. So if you read an electric iron, 15 kilowatt, well, kilo means 1,000, and the unit of, first of all, if we look at this equation, for kinetic energy, the unit is joules, and if we calculate the unit for work, it's going to be joules, so they have the same unit. And of course, for potential energy, still, since it's energy, the unit still joules. And for a power, the unit will be a joule divided by a second. And that's what we call 1 watt. And in technical applications, people sometimes use an old, outdated unit of power, horsepower. 1 horsepower equals 760 watt. That's the conversion factor. So if you read something and it says horsepower, that's it. That's conversion factor. This is a definition of power. This is an equation we can use. How did we get this equation? Well, from a definition of work, divide by time, displacement over time, velocity. That's it. So this is the magnitude of the force acting on an object, instantaneous velocity, angle between velocity and force. Question. To this day, physicists believe that there is no negative mass. There are some theories about that, but still, if the mass is positive and anything squared is positive, kinetic energy is never negative. What do you think about force, gravitational potential energy? So I know your answers are there, but just to save time, if you answer yes, please raise your hand. No? See, you're against everybody. What is it about? It's about this. We've said many, many times that even if we choose the axis upward, the choice of the origin is up to us. We can choose it anywhere, 0. This variable has to be measured relative to the choice of 0, and we can choose it on the ground, on the bench, on the roof, anywhere. So for the same object, depending on, so this is the object. For the same object, depending on how we choose the origin, y could be positive, here relative to this origin it's actually negative, y could be negative, or the same object, below 0, above 0, y could be positive. That's it. So positive number, wherever it is. Could be positive, could be negative, could be even 0. Just remember that. Depends on the choice of the origin. So, again, a definition of work with a picture. This is the angle we have to use. A displacement is a vector. We know that. It's an arrow which just points from start to finish. It doesn't matter how the object has been moving. And the force is a vector. And because we cannot use this equation for a force which changes, as long as force is constant, again, it keeps the same direction. So this angle is a fixed feature of the situation. Question. So now it's time to draw a picture. You have to see very clearly two directions. One direction, which is represented by the force, the first variable in that equation. Second direction is represented by displacement. You need to see those two arrows. And then by looking at those arrows, you will see the angle. And when you see the angle, you will be able to answer this question about work done by the normal force. So you gotta be drawing an object. For that object, you need to draw only, for this question, for that object, you need to draw only normal force, because the question is about normal force only. You don't need to see anything else. For that object, you also need to draw the displacement. So, how does displacement point? To the right, exactly. And how does the normal force point? Normal force. How does it point?
Points down.
Normal force
Or points up, sorry.
points up, yeah, points up. So one direction is straight to the right, second direction is straight up, correct? So what is the angle, do you see, between these directions? 90. What is cosine of 90? 0. This is the type of 0, 0. Yeah, you can check. This is the type of reasoning which we have to go through every time when we need to apply this equation. That's it. Any questions? So in general, because the work depends on the angle, it could be a positive number, negative, 0. It depends on the angle. Because first two variables are magnitudes, only angle influences the actual value. When angle is 90, no work. The force is acting. The force is not 0, but it doesn't do any work. The work done by gravity. Well, this is something we have learned, and we've talked about it extensively. This is how it moves. So if we take two photographs, two snapshots, initial location, final location, it doesn't matter what has been happening in between. We know force of gravity, mg, is constant, so we want to use this equation. mg, fixed number. This is supposed to be the magnitude of the displacement. The displacement is a vector which starts here, ends there, a straight line with a pointer. That's the force of gravity. Always points down. So according to our definition, that's supposed to be the angle we have to use in this equation. But, as we know, when we see a right triangle, we can use it. In this triangle, this is a hypotenuse. In this triangle, this doesn't matter. In this triangle, this side is equal to hypotenuse times cosine. So hypotenuse times cosine is equal to this. So we can always use the original equation for the work done by force of gravity, but turns out there's a much easier equation. The work done by a force of gravity on any object always equal to the product of the mass of this object, g, and the difference between initial height and final height. So when the object falling down, initial, final, initial minus final, positive number. Gravity does positive work. And positive work means kinetic energy changes positively, increases, the object is speeding up. Now, when the object is traveling upward, initial height, final height, small number minus large number, this difference is negative. So gravity does negative work. It slowing down decreases kinetic energy. And this works for any type of the projectile motion or for any motion when height might be involved. Yes?
What you said about if it's positive or negative.
two situations, very quickly. Moving first, okay, it doesn't matter. Moving upward, moving downward. Moving upward, initial is less than final. Moving downward, initial is greater than final. So for the gravitational potential energy, if we apply this equation, which always equal to this, the result depends on this difference. For this case, when height increases, this is what gravity. This is what it actually is. I didn't mention that, and I should have, because mgy initial minus mgy final. If we go back several slides, that's exactly what we called gravitational potential energy. So this is gravitational potential energy initial minus gravitational potential energy final, or people write it like this, minus delta U, or minus delta GPE. Because delta means final minus initial, but we need to subtract initial minus final. All right, so here, and for this situation, the work of gravity will be positive. And when height doesn't change for the horizontal motion, the work of gravity will be zero. Gravity does work only when height changes, positive or negative. Positive means it's speeding it up. Negative means it's slowing down. Zero means it doesn't affect speed. So, as I just said, for the gravity, the answer should be zero, but only in this situation, because the height remains the same. This is 90 degrees angle. Or if we apply the second equation, initial height is equal to the final, so we're subtracting same number, zero. Now, a work done by something we apply. Yeah, we can apply a tension, we can push on it. In this situation, we're pushing and make it travel horizontally, right? So again, if we push, still there is force of gravity, there is no more force, friction applied, 4 forces, so technically we can calculate the work 4 times for each force. And we just said for the normal force, the work is zero. For the force of gravity, the work is zero. Now, applied force, let's do it quickly. Again, if we need to calculate the work done by applied force, we don't really need the whole diagram. We just need that force. And we need a displacement, because we want to apply the equation on a screen. Magnitude of the force, magnitude of the displacement, cosine of the angle between force and displacement, magnitude of the force. We are applying the force which has magnitude, given magnitude 14, the angle 60. Well, that is the same angle, so I just put it here, 60. We moved it 2 meters to the right. So all we have to do is just plug in everything we can. What number should I write for the force? Someone need to say something. Thank you. What number should I write for the displacement? What number should I write for a C? Say something. I'm not giving up on you. So this is a variable C. Do I replace it with a number? So why are you so not sure? No, it's a stupid suggestion. This is a part of an unbreakable geometrical symbol, C or S. We don't replace it with anything. Okay. What number should I write for theta? Actually, that's what I'm doing, numbers here. What do we do now? Calculating. Take calculator, calculate. So please. Cosine of 60 is a half. 14. 14 what? Joules. Now, just to remind you that technically, every time when we need to see an angle between two arrows, the first step is to redraw those arrows in such a way so they would start from the same point. We're not adding vectors, we're measuring an angle. That's a different procedure. So now you can see the angle. Sometimes if you don't do this, you may misread the angle. All right, friction. Technically, this is the only expression you need. This is just for curious people. How do we arrive at this expression? The thing about friction is that no matter what's happening to the object, friction always opposes the motion. If velocity points to the right, friction points to the left. If velocity points to the left, friction points to the right, etc., etc. So no matter what is happening to this, the angle between velocity and friction, always equal to what? What is this angle equal to? 180. And cosine of 180, always -1. That's it. So it's a good thing about friction. We just need to remember the work done by friction should be always negative. This minus is cosine of 180 degrees. But what it should be equal to? Well, according to a definition, it's force times displacement. If trajectory is complicated, all we need to do is just break it down in smaller portions. So small displacement here, small work done here, plus work, plus work, plus work, plus work, plus work. In the end, what we have here is not displacement. It's actual distance traveled. So for the friction, the equation looks like this. Well, that's the force of friction, yeah. Coefficient times normal. And that's not a displacement. That's the actual distance traveled. Because if we move this box 1 foot to the right, there is a certain amount of work done by friction. But if we moved it like this, friction has been acting longer distance. So the work done by friction is different. And of course now, a question. We pushed the box. The initial speed 5. The coefficient, that's what we call mu, is 0.4. 0.4 of what? Nothing, it's just a number. And we need to calculate the work done by friction. Well, the work done by friction should be equal to this, cosine of 180. times this product, which is magnitude of force of friction, times distance traveled. So this times this times. We've done this part of our reasoning many, many times before. So please tell me, how can we calculate quickly normal force? In this case, it should be equal to what? mg. mg 15, g 10. So the only thing we don't know here is length. But we knew it, right? So all we have to do is just go back and find it. Not yet, not yet, not yet, not yet, not yet, not yet. 3.125. Same box, same initial speed, same force of gravity, same planet, same coefficient, so same number for the length, 3.125. So negative 0.4 times 15 times 10 times 3.125 is equal to? Doesn't matter. Negative?
183.7.
Joules. Joules. Any questions? Yes? It's not a question to me. I'm just following the rules. Why is it negative? You should ask someone with a higher power. If the angle is above 90, cosine of that angle always negative. That's what calculator tells you. So maybe you should talk to your calculator. We just have to follow the rule. The work is a product of three numbers. What you confuse is the work which you used to do like a human being, and that term which is reserved in physics for the product of three things. In real life, when we do something, we always consider it's positive because we love ourselves. In real life, sometimes when we do something, it actually affects other things negatively, right? So same here. Well, we just have it proved. In this particular situation, it is negative. Physical meaning of work being negative is it tries to slow it down. When several forces acting, each does work. If work turns out to be zero, that means that force doesn't affect speed at all. If the work is positive, that means that force tries to speed it up. When work is negative, that means that force tries to slow it down, and whichever wins, that's happening. If the overall work is positive, the object is speeding up. When overall work is negative, the object is slowing down. And these are your examples. Slowing down, gravity does negative work. Speeding up, gravity does positive work. That's it. That's all it is. Well, okay. So, final kinetic energy clearly is zero. It doesn't move anymore. Initial kinetic energy initial should be equal to m times v initial squared over 2. That should be equal to 15 times 5 squared over 2. 0.87?
187.5.
187.5. So now you can see that these numbers are very close. Well, I don't know. These numbers are very close. There is margin of error due to rounding up. So this is a confirmation of that equation, of that law I've mentioned before. Kinetic energy final minus kinetic energy initial should be equal to the net work. And hence, in this situation, 0 minus, well, 187.5 is about negative 183.125 plus 0 plus 0. Yes? Whatever you say. Works for me. 7.5. All I need to do is just move this stubborn decimal point. Well, anyway, sometimes it's not going to be exactly the same, especially in the lab, because measurements are never as accurate as our examples. But this is, again, a specific illustration of this particular relationship. Again, it's very important relationship. That's why it has a name, work kinetic energy theorem. Change in the kinetic energy, change in the kinetic energy always equal to the net work done on any object. And we can use this backwards and forward. We can use it for calculating total work, or we can use it if we know work for calculating energies, kinetic energies, doesn't matter. Okay, I just did this. Now, a new definition, probably last for today, mechanical energy. So this is what we call kinetic energy. It's related to the motion of an object. For a moving object, it's never zero. This is what we call potential energy, specifically gravitational potential energy. If we add kinetic energy and potential energy, the result has a name mechanical energy. That's it. What's good about it? Well, this is what's good about it. Only friction changes mechanical energy. When there is no friction, when we neglect friction, mechanical energy doesn't change, remains constant. We call it conserved, and only friction changes. So this term represents the work done by friction. Well, see, I've got something here, which means there is a more general approach. It's not just about friction, but we don't talk about other options which might change mechanical energy. Here, we just need to remember if friction is not acting, if this term is zero, mechanical energy remains constant. If friction is acting, mechanical energy changes, and friction always decreases it because it's negative. And this expression, kinetic initial plus potential initial plus friction equals kinetic final plus potential final, has a name, law of conservation of mechanical energy. Now, if you're curious enough, you can do some algebra, and you can prove that work kinetic energy theorem and law of conservation of mechanical energy is exactly the same equation. It's just rearranging numbers. And what you use what you want to use depends on your personal preference, convenience. That's it. And we're going to do examples. Yes, that's another name you may read sometimes for the law of conservation of mechanical energy, master equation, because it comes from the master. I mean, Newton, Isaac Newton. Well, I think it's time. What happened to my alarm, I don't know. But yeah, officially we're done for today. This is a specific example. We're going to do more problems starting tomorrow. No labs today. The lab is tomorrow and after tomorrow. This week we won't have only one lab. So again, I'm going to post the solution to the exam, check it. I have my office hours today and tomorrow. So please, if you have any questions, see me. And if you didn't pick up your exam at the beginning, please, it should be alphabetical.
I think there was an error in adding up my points.
Maybe it is possible. If it's just adding,
So, I think the problem 6.
if it's just adding, this is what I wanted to do. Is the fastest way. Write your BUID here. Write your BUID
Yeah, it's problem
there.
6. Yeah.
Take a picture of this, take a picture of that, and email it to me.
Okay.
Because yeah, if this is just a math, I can check it
Yeah.
without using any time.
Okay.
Good morning. Yes.
This is a really minor thing, but when you're writing on the board, do you think you could use a darker color than the light green? Because it's just kind of like hard for me to see.
Green?
Yeah, like that's kind of light on the board from the back. Maybe I'm colorblind or something weird. But like the red you use is good.
Okay.
Dark blue is good. That green is just a little bit light.
What about like this?
Yeah, that's darker.
Yeah.
That's darker. Looks better.
No problem.
Thanks.